So I think by now everyone knows that artificial neural networks are really compelling for a growing class of computer vision problems as well as problems in other domains. But they're also really challenging for a number of reasons, including and especially the fact that they tend to be extremely computationally demanding. And so, if you load up your CPU or GPU or DSP with a convolutional neural network, if you can get sufficient frame rate, it's likely to be an unacceptably high power consumption. So that's a key problem for the industry right now. And fortunately, some very bright people are working on this problem. And Professor Vivian See from MIT is one of these people, along with her colleagues at MIT. And I'm really pleased that she's come here today to share with us some of the highlights of her work on creating energy-efficient hardware architectures for implementing artificial neural networks and other vision algorithms. Welcome.
Great. Thanks, Jeff, for the introduction. All right, so I lead the Energy Efficient Multimedia Systems group at MIT. We look at dealing with large, high-dimensional data in an energy-efficient manner. So I'll just first go through by motivating what we focus on. So in our opinion, video is like the biggest form of big data, right? So just some statistics, which I'm sure you've all heard of. For instance, if you think of communication, video accounts for 70% of all today's internet traffic. So basically 70% of all bits that flow through the internet is representing a pixel. If you think of the amount of video content that's being generated, just from the consumer level, over 300 hours of videos being uploaded to YouTube every minute. Actually, this statistic is 2 years old, so now you can imagine that number is much higher. And also Facebook is a lot of video now too, not just YouTube. And then also over 500 million hours of video is collected for video surveillance every day worldwide. So that's a huge amount of video. It's obviously not feasible for people to watch it in person. You need computers to watch it, or some form of machine to process it automatically. A lot of this video is collected on battery-operated devices like your phones, your tablets, even drones. And ideally, you'd like to do the processing and understanding of the video content on the phone itself, on these embedded devices themselves. But obviously, one of the issues is that the energy there is limited due to the battery capacity, right? And the battery capacity is limited due to cost, size, and so on. So often what happens is that we compress the video, and we push it onto the cloud for processing, but even on the cloud and in the data centers, the amount of processing that you can do there is limited in terms of power and heat dissipation, right? So regardless of where you're processing this video, either locally or in the cloud, you really need energy efficient pixel processing. And that's kind of the motivation of the work that goes on in my lab. In particular, when we talk about pixel processing, there's two types of processing that we care about. So the first is compression. So if you're going to store or transmit video, you're going to have to compress it. And this has been increasingly challenging just because of the amount of video, but so you need to have high coding efficiency, which means same amount of video, same quality, fewer bits. But in addition to that, you also need to improve the speed, just because of the amount of video, but also because the resolutions are increasing, right? So you need to be able to encode and decode in real time at these ultra HD resolutions. And then of course, energy efficiency is really critical because video is a must-have feature on these energy constrained devices. But looking forward, what we also care about is not just compressing the pixels, but ultimately what we want to do for a lot of applications is understand the pixels themselves. And so the goal here is to not just compress, but to understand. And the question that we have, and which will be the focus of today's talk, is whether or not we can make computer vision as ubiquitous as video coding. We know all cameras out there have some sort of video compression on them. Can we make it so that computer vision is as energy efficient as video compression, so that all cameras out there can have some form of intelligence on it and tell you what it's actually seeing? So that's kind of the overall motivation of today's talk, and we do that, the second goal. When we talk about computer vision, there's a wide range of different forms of computer vision. For today's talk, we're going to focus primarily on object detection and classification. And in that kind of task, there's typically two classes of features that we need to deal with. So the first is what we call handcrafted features. These are the more traditional kind of features that have been around for a while. We're looking at histogram of oriented gradients, so looking at the edges of the image themselves. And then also, and then also looking, so that's like a Hog feature, and this has been around since 2005, and then also looking at deformable parts models where you can detect different parts of the model themselves and let them deform, and it improves your accuracy. Then we're also going to talk about trained features, specifically deep convolutional neural nets, which recently have provided much higher accuracy than the more traditional approaches. But what we really want to focus on here is the trade-off between energy efficiency and accuracy, right? So shown here on the graph at the top, right? So we're going to look at, first of all, how energy efficient can we make the handcrafted feature approaches, and then gradually add on more complexity for the deep convolutional neural nets. Just to as a high-level summary in terms of how we approach these problems in my group, or at least for this form of work, the first thing that we want to do is joint algorithm and hardware design and optimization. So in the past, you design the algorithms, you throw it over, and let the hardware designers do it. We do both in my group. So as an example of this, what we want to do is you want to make the algorithms, you want to use the algorithms to make the data sparse, for instance, and then you want to design hardware that can exploit it. We also want to minimize data movement. You're going to see that basically data movement, reads and writes from memory, costs much more energy than the actual computation themselves, and that's actually where we should be focusing. So we want to maximize data reuse and leverage things like compression. And then, of course, we also want to balance things like flexibility and energy efficiency. Right? You want to have hardware to be configurable so you can use it for many applications, but you also need it to be energy efficient. So how can we balance those needs? All right, so the first thing I'm going to talk about is you're going to start simple, looking at a Hog SVM accelerator. This work was done by my student Amar Suleiman, and we published it last year. So just very quickly, I'm going to go through kind of the object detection pipeline. So you have an image, which is a set of pixels. You go through feature extraction. In this particular case, we're looking at Hog features, which are handcrafted features, in kind of like a raster scan order that we're going to scan across. Okay, I guess it's not working. We're going to scan across the actual image itself. Once you extract the features, let's say X, you would do a dot product between the features and some weights that you've learned from a large data set. And these, based on the dot product of the weights and the features, you get a score, and then you compare the score to a given threshold. Obviously, if the score is above that threshold, you've detected an object. If not, there's no object there. And from the detection, not only do you, know where the object is, but also what the object is as well. So this is normally a video, but since we're not showing it, but basically the motivation of this video is to show, we not only need to detect objects at a single scale, but multiple scales as well. This is important because objects have different sizes, and they can be at different distances from us, so we need to be sensitive to that as well. But we also, that's something we need from an accuracy point of view, but from, implementation cost, it doesn't come for free. So for instance, the way in which we address different scaled objects is actually we take an image and we generate an image pyramid, meaning, we scale up or scale down the size of the image for different scales, and then basically pass the template across the entire pyramid to detect different objects. So basically the higher scales, you can detect larger objects, and then the lower scales, you can detect objects that are further. So this is actually one example of how computer vision is different from video coding. In video coding, you don't really have to go to this high dimensional space, right? This is already you're projecting into a larger space than you would have to do if you were just doing compression. In kind of the trade-off experiment that we did, this is for the INRIA person data set, we see that for 12 scales, we get about a 2.4x increase in accuracy compared to single scale, but this does come at a cost of a 3.2x increase in processing, so it's not for free. But this is already kind of trading off accuracy for processing. The one thing that does help for computer vision that is not present as much for video coding is parallelism. So many of these computer vision tasks are highly parallel. So we can really exploit that. So the one way we can do that here is actually use multiple detectors in parallel. Of course, the cost of parallelism is that you're going to increase the area, right? So we want to have a nice balance between area cost and energy cost, or area cost and throughput. Another thing I should highlight is that as you increase the throughput, what you can do for ASICs is you can actually scale down the supply voltage, right? So as you have more parallelism, you can operate at a lower voltage, and that's what we're showing here. So let's say for a fixed throughput of high definition 1080p 60 frames per second, if we have one detector, we don't have to run it at 1.1 volts. If we have 3 detectors, we can run them at 0.72 volts, and then at 5 detectors, you can go all the way down to 0.6 volts. right? Because the trade-off of going to lower voltage is increased delay. But of course, you also have increased area. So we found that through this energy versus area trade-off, having 3 detectors at 0.72 volts gives us kind of the best balance between those two costs. Another thing we want to factor in is that we want to make sure that the workload for each of these detectors is balanced, right? Because there's no point of having a lot of parallelism and having all of your work land on one detector. So we distributed, this is just an example of how we distributed the different number of pixels per scales across each of the detectors. So for example, the first detector has 1 full large scale, and then the next detector has 2 scales, and so on. So using these approaches, we can use 3 parallel detectors operating at 0.7 volts with a balanced workload, and we're getting about 3.4x energy reduction by doing this. Another thing I just want to highlight too is that you don't want to just always blindly parallelize everything. So as an example here, we have 3 detectors running in parallel. But what we actually want to do is we want to share, so what they're, these are all doing feature extraction and classification. But if we actually synchronize all of them so they share reads from the weight memory, which is like the weights for the classifier, we can actually reduce the energy consumption there. And as I'm going to continue to highlight, data movement and memory reads are actually more energy costly than the actual computation themselves. So by synchronizing all of these detectors so that they read the same data from this weight memory, because this weight memory is just the template at the same time, we actually get a 20% reduction in power consumption. Right? So don't blindly parallelize. You want to think about how you're using, what data can be further still shared across these detectors. And then finally, one of the innovations that we had here was looking at the data itself. So if we take an actual image coming in and we generate a histogram, it would look somewhat like this. So this is the intensity and this is the count. It's pretty widely distributed. What we can do though is if we think about what we're actually trying to do is we're going to take the gradient and like compute the hog, right? So why not take the gradient very early on, even before you generate the image pyramid? Taking the gradient very early actually changes the histogram so that most of the values become 0. And also the dynamic range of the values becomes overall quite a bit lower. Right? So the advantages of this is that we can actually use fewer bits to represent the dynamic ranges, and then the values of 0 means, and from a circuit point of view, you have less switching, meaning you're going to dissipate less power. You go, like the buses go on and off less frequently. So overall, by doing this, by doing gradient processing at the very beginning, you can actually reduce your memory size by 2.7x. You reduce your power consumption by 43%, and then there is some impact on detection accuracy, about 2%. So that's the overall trade-off. And what's really exciting here is that there is ongoing research. We haven't done it in my group, and other groups where they're looking at, obviously the output of the image sensor being just the gradient itself. So this could be definitely exploiting that kind of behavior. So just to summarize this work, so overall this is a real-time hog detector that it basically runs real-time, 1920 by 1080 at 60 frames per second. It supports multi-scale, which gives us 2.4x higher detection accuracy, and then the low power features that we had in terms of parallel detectors, voltage scaling, and gradient preprocessing give us about a 4.5x energy reduction. And these are all obtained from post-layout simulations. This is just a image of the actual layout itself. This is in a 45 nanometer SOI technology. And so overall, the system is doing real-time multi-scale object detection at 45 milliwatts, which maps to about 0.36 nanojoules per pixel. So some of you in this room might be like thinking, what does 0.36 nanojoules per pixel actually mean? So remember, one of the metrics that one of the goals we're trying to achieve in this work is to see whether or not we can make a computer vision task like object detection as energy efficient as video compression, right? Because we want to enable it to be very ubiquitous. So we can compare this to the energy per pixel for various video codecs, both H.264 and 265 encoders and decoders. And you can see here on the left-hand side in blue, the energy per pixel for video codecs typically are around 1 nanojoule per pixel plus or minus half a nanojoule, so 1.5. And so you can already see with this approach here that we've taken with the hog detector, with the low power features that we've introduced, it's already consuming less than a nanojoule per pixel. It's already on the same order of magnitude of video compression. So this means that for the same energy as it takes to just compress the pixel, we can now tell you what's actually in the image and where it is in the image. And this is at high definition. So this is very exciting. So what do we want to do? Well, we're going to push accuracy up even more, right? So this is the basic thing. How much more can we do? So now what we're going to look at is deformable parts models and how do we build a hardware accelerator with this. Again, this was work done by my student Amr and Jendong. And this was presented at VLSI 3 months ago. So we're going to talk about deformable part models. This was work that's been published by another group back in 2010, and it was widely popular before CNNs came into play in 2012. But the key idea here is that basically you still use Hog features, but now you break up the image to not just kind of a root template, which is basically the silhouette of the person, but now you also want to detect the head, the arms, and the legs of the person, for example. And this allows you to, the person be in more different poses. So in terms of when you compute the score, you have the root score, which is how you typically do it, but you'd also have a part score for each of the parts of the person. And then you also want to factor in a deformation cost, right? Because obviously you would expect the head to be at the top of the person. If it's like very far off, something terribly wrong has happened, so you want to factor that into the overall score. So that's the deformation cost. And by doing this, you can actually get double the accuracy compared to using a rigid body template, which is what we saw before. But there is, of course, the cost here. Right? We care here about embedded vision. The cost here is there's going to be a high classification cost. So if we just look at the overall pipeline again, basically what's primarily changed has been the classification part. So the feature extraction is the same. And the classification parts, now you have to do processing you have to learn weights and then use the weights for the roots, the parts, and the deformation. So what we're going to do is look at, so in terms of summarizing, what is the overall complexity here? We're going to compare flexible to rigid. So if you have a deformable parts model classification with 8 parts, it requires over an order of magnitude, so we computed around 35x more operations than doing the root or the rigid body itself only. This is due to the fact that you have the parts template, so you have to do all the little body parts. They also have to be at double the resolution. And then you also have the deformation computation. So the approach that we take to reduce complexity here is twofold. So the first thing we want to do is what we call root pruning, and we want to actually reduce the number of classifications that you perform, right? So we want to reduce the number of parts classifications based on the root. I'll talk a little bit about that. And then the second thing that we want to do is what we call basis projection, where we can reduce the number of computations per classification. Okay, so the first one is reduce number of classifications, and then the second is reduce computations per classification. In terms of reducing the number of classifications, what we do is basically, if we start off with, let's say, these 5 images and we're looking for a bike, what we would first do is do the root classification on it, rather than doing both at the same time. And you can see that you can already eliminate the first 3 characters. This kind of looks potentially like like a bike, so you can keep it. And then only after you get a decent score with root classification do you then apply the parts classification. And then you can see that you can resolve that this is the actual bike itself. Right? So what we can see here is that you can obviously adjust the threshold when you prune the actual root candidates to go to parts detection. And as you increase the pruning, obviously you get lower detection power, but the accuracy also drops. We actually found that up to 80% there's almost no impact on the classification. This is for the VOC 2007 data set. Actually, up until 97%, it's less than a percentage impact as well, so you can do that. Because of time limitations, I won't go too much into this, but one of the costs of doing this type of a pruning thing is that the parts that are now dependent on the roots, you can no longer process them in parallel, so you need to have some kind of storage because you're introducing this dependency, so we use vector quantization to reduce the overall storage on chip. The second approach that I was talking about is to reduce the number of computations per classification. And so what we do is we actually project the data into a different space where the data becomes more sparse. So just as an example, if we look at the weights, these are the classification weights. In the original space, they had a histogram that basically looked like this. Only 7% of them were zeros. Once we projected into a new space, about 56% of them were zeros, and obviously we skipped those computations. And this gives us about a 1.8x reduction in power consumption with no impact in terms of accuracy. So we actually built this test chip. This is fabricated and measured results in a 65 nanometer technology. It's around 3.5 by 3.5 square millimeters. It does high definition at 30 to 60 frames per second, and it can do 2 classes at the same time. You can just program it to do 2 whichever classes you want at different scales. And overall, the optimizations we did introduced, you got a 5x power reduction, a 3.6x memory reduction, and then about a 5% decrease in accuracy, and that's due to the vector quantization. We believe that if you retrained based on that, then you can eliminate most of that. Again, if you look at the overall power consumption, we're around 1 to 2 nanojoules per pixel. If you're at 30 frames per second, you're at 1 nanojoule per pixel. So again, when we stack it up to the other benchmarks comparing to the other video codecs, we're still now at a place where we're comparable to video coding, and these are measured results, right? So this is very promising. So now we want to push it again even more and go towards deep convolutional neural nets. This is a project that we called IRIS. We had a bunch of press about it this year. It was published. The chip itself was published in February at ISSCC 2016, and then the data flow we're also going to talk about was published at ISCA, and this work is done primarily by my student Yushin Chen, and then we had a postdoc, Tushar Krishna, also helping out, and then my co-PI is Joel Emmer on this. So I'm just going to briefly walk through deep convolutional neural nets. I know a lot of you might be familiar with it, but I just want to emphasize why is it challenging, right? From an energy point of view, why should we care? So deep convolutional neural nets, the idea is that you have many convolutional layers. These days you have publications that go up to thousands of convolutional layers. I'm assuming I don't have to motivate why it's very accurate, right? You guys all believe it's accurate. And then you finish off with 1 to 3 layers of the fully connected, right? So what you need to take away here is that the convolutions parts account for most of the computation and most of the runtime and energy consumption, over 90% of it. So that's what we're going to focus our efforts on. How do we minimize the energy consumption of convolutions? So we start out with, so convolutions is something we've seen in image processing for years. So why is it such a big deal? So we'll start out with an input image or a feature map if you're in the middle of the network, and a 2D filter. And so basically what we always do for convolutions or 2D convolutions, you take the element-wise multiplication dot product of these two, and you sum up the values and you get one output, right, pixel. And then by convolving it, you kind of do like a sweep across, doing a sliding window, you generate another pixel. So this is like nothing special, again, just regular image processing. Where it becomes more challenging for deep convolutional neural nets is we increase the dimensionality. So in addition to the 2D convolution, you also have to factor in a third dimension, which is the input channels. What are input channels? Just to give an idea, so at the very input of the overall, what are channels? At the very input of the overall network, a channel could be thought of as like red, green, and blue, right? So at the very input of the network, you're talking at 3 channels. But soon, for example, AlexNet was a very popular neural network. It will expand to 192. So you can see the dimensionality will increase. And what happens here is that basically on each of these channels, you do a 2D convolution, and then you sum across all the channels, and you just get one output value. All right, so that's the third dimension. And then you have this fourth dimension, which is that you actually want to apply many filters to the input image, right? And each of these filters will generate one output channel. And the number of filters you have, again, if we use AlexNet as an example, is between 96 and 384 filters. So that's why it becomes much more challenging than image processing. And then, of course, in many applications, you're talking about many different images that you would want to process in the same way. So the key thing I want to emphasize here is that when you're talking about deep convolutional neural nets, you need to build hardware that can support the large size of these filters. And then also, so we're talking about, as I mentioned, hundreds of filters, hundreds of channels. And then also per layer, the size and the number of filters and the number of channels can vary. So your hardware must also have the flexibility to support all of this, right? So you need large sizes, and you have to be able to support varying shapes. So that's one of the main things I want to emphasize. And of course, at each layer, you're dealing with tens of thousands of parameter weights, and then also hundreds of millions of multiplies and accumulates. So there's a huge amount of compute. There are some things that we can benefit from. So the first thing is these operations are highly parallel. So we can achieve high throughput. That's fairly easy, right? Just do a lot of multiplies and accumulates at the same time. But what really is the challenge in terms of both throughput and energy efficiency is memory access, right? So if you have a multiply and accumulate here, you need to read in 3 pieces of input. So you need filter weight, image pixel, and the partial sum when you're accumulating, and then you have the updated partial sum at the output. In the very worst case, if you're reading this from an off-chip DRAM, the energy consumption from reading and writing to the DRAM is at least 200x more than the multiply and accumulate on chip. So in the very worst case, you're talking about 700 million max, but you're talking about 3 billion reads and writes from the DRAM. So that's huge, big issue. Fortunately, there's some opportunities for data reuse that we can actually exploit. And this can actually reduce the amount of data that you have to read from off-chip, or once you read it on once, you can reuse it multiple times. You don't have to read it multiple times. So the first example is what we call convolutional reuse. When you're doing convolution itself on a single channel, you're going to use the filter and the image pixels over and over again, but just in different combinations. That's what convolution means, right? You also have what we call image reuse. Remember we talked about multiple filters being applied to the image? Well, if you applied multiple filters to the same image, that means you're reusing the image pixel across multiple filters. And then finally you have filter reuse, where you're applying one filter to multiple images, right? So you're reusing the weights there. So we really want to exploit this. What we want to do is to store these values in low-cost memories and then read them from there instead. Also, I just briefly want to talk about the different compute paradigms people typically use. So there's the temporal architecture, which is like SIMD and SIMT that you'd find on a CPU and GPU. And the idea there is that you have a bunch of these processing units. They all share the same control. They're all doing the exact same thing, and they're all sharing the same memory. In our work, what we actually want to do is use a spatial architecture. The idea is that we have an array. So we have an array of processing elements. Each of them have their own control and own local memory. And then they can talk to each other. And then finally they can go to the memory hierarchy. So having local memory allows us to have efficient data reuse. We're going to talk about why this local memory is cheaper. And then being able to talk amongst the processing elements also enables you to avoid going to the memory hierarchy, which is more expensive. And by local memory, I'm talking really small memories here, so like 0.5 to 1 kilobytes of data. Okay? And so the question is, if we choose this architecture, how can you take this really high dimensional problem and map it onto this spatial array? Like there's very limited memory here, so how can you cut out a small piece of this large problem and map it on? And specifically what you want to do is increase reuse of the data, particularly the weights and the pixels, and then you want to maximize local partial sum accumulation. Okay, it's a little bit fast, but okay, so we're talking about the data flow itself, so the mapping, how you take this convolution and map it to the spatial array. So again, we have this overall architecture here, right? So we have the processing elements, right? Each of them basically have a multiply and accumulate and a local memory and what we call register file. Then they will talk to a global buffer, and then the global buffer will then talk to off-chip DRAM. Now, the thing I want to emphasize here obviously is that data movement is expensive in terms of energy, right? So if we look at the energy consumption of an ALU, let's say it's 1x, reading from a local memory, and that local memory is quite small, between 0.5 to 1 kbytes, it's also 1x. Reading from a processing element, a neighboring processing element, using basically the NOC, it's like 2x. Going to the global buffer, which is typically 100 kilobytes or larger, is going to be 6x. And then going off chip, like we talked about, is 200x. So you want to have this data flow that basically maximizes data reuse for these lower levels and low cost memories. You want to do most of your reads from the cheap memories as much as possible. So as you all must know, that there's tons of publications in this area recently. So the first thing that we wanted to do was kind of define a taxonomy to classify the data flows of all these different forms of work. So it gives us a way to think about, all the stuff that's out there. So there's various options that you can do. So the first approach that we call is weight stationary. So the idea here is that we want to, in each of these process elements, in the local memory there, the register file, store a weight, right? And so that way, this minimizes the read energy of the weight itself. The weight is being read from the cheapest memory that you have. However, the trade-off of that is that, of course, you can't do that for all types of data. So both the pixels and the partial sums then must flow through the network and come from the global buffer. So it's a trade-off. You're minimizing weight energy, but the other forms of data are moving around. The alternative strategy is saying, okay, I want to forget about the weights. I want to minimize the energy cost of my partial sums. I don't want those to float around. So what I'm going to do is what we call the output stationary approach. And each of these processing elements computes basically one output. So all those partial sums that need to be accumulated, they don't flow through the network or the higher level of the memory hierarchy. They try and stay local as much as possible. So here we're minimizing the read and write energy of partial sums. Okay? Another approach that people have taken is what we call no local reuse. So the idea here is that there is a cost to having all these small local memories, which is that the area per bit is less efficient, right? So One strategy is to say, forget about all these small little memories distributed everywhere. I want to allocate or aggregate all of that area and use it for my global buffer where my area per bit is much more efficient. And so the overall storage capacity of my chip is going to be much higher. And this enables us to reduce DRAM reads and writes. But of course, the trade-off here now is that you have a lot more traffic in terms of weight, pixels, and partial sums in your network and from your global buffer. So the approach that we take is what we call, so those three, so that was weight stationary, output stationary, and no local reuse. Those are existing works. And so the approach that we take is what we call the row stationary approach. So again, we have this example, 3x3 filter by 5x5 input image, and then you have an output image. The idea here is that within each processing element, we're going to do 1D convolutions. We're going to take 1D of the filter, 1D of the input image, and do the convolutions locally. So I'll just shift it through. So you have the register file. You basically put one row of the filter in the register file, and then you kind of do a sliding window across one row of the input image. And so as you can see, as you go across, the first time you're reading 3 in, but at all the other cases, because you're exploiting convolutional reuse, you only need one extra input value coming in to generate one extra output value. So we're maximizing convolutional reuse at the register file, and then we're also maximizing partial sum accumulation at the register file. Right? So you're not moving data around. So within each processing elements, you're completing a full 1D row convolution. Of course, you're going to say, well, we're dealing with more than 1D, so how do we expand this? So if we have one processing element that's doing, one row of filter, one row of input image. What we do is that we can do multiple processing elements. Each of them are doing one row each, right? So as shown here, so we've expanded from this to this. And then we accumulate vertically and sum them all up, and we generate one final output row, okay? And then we can do the next row would be the same filter, except now you notice that rather than doing rows 1, 2, and 3 from the input image, you're doing rows 2, 3, and 4. Right? And then you sum them up, you generate row 2, and then you repeat that. Now you're doing rows 3, 4, and 5, and generate row 3. So what's the benefit of doing this? So the first thing is, remember, we want to avoid reading from the higher cost memories, right? So now what's happening is that every single time you read one row of the filter, you're going to reuse it horizontally across all the processing elements, right? So one read, you satisfy multiple processing elements. Similarly, for the image rows, you read once, and you can reuse it diagonally across the array of processing elements. Right? One read, you can service 3 processing elements or more. And then finally, all the partial sum accumulations, you're doing that all again locally in the array, so you don't have to go to the global buffer every time. You only push it after you have basically the final value, you push it to the global buffer. So that basically exploits all the 2D kind of convolutional reuse that you can do within the array. Given the time limitation, I'm not going to talk about the other dimensions, but the overall idea is that within each of these processing elements, you can map multiple images, multiple filters, and multiple channels so that you can have more reuse. So you can minimize the data movement overall. So just to compare all these different data flows, again, weight stationary minimizes movement of filter weights, output stationary minimizes movement of partial sums, and then no local reuse maximizes global buffer size. And then we have our row stationary approach. We use an energy model just based on the one that we presented before. This is for same total area. They're all doing AlexNet. They all have 256 processing elements and a batch size of 16. So just comparing the overall energy for convolutional layers, you can see that the row stationary approach is 1.4 to 2.5x lower energy. The things I want to point out here are that, first of all, you can see that majority of the energy is consumed by the register file, and that's by design. We wanted most of the reads and writes to be from the register file. The other thing I want to highlight is that, and the ALU power is the same for all of them. They're doing all the same compute. And also is that even though no local reuse has the highest capacity and the lowest DRAM power, overall it still doesn't have the lowest power. So you need to balance not just DRAM power, but overall chip power as well. Right? You don't want to focus on one or the other, but both. So doing minimum DRAM power is also not enough, but also you must also consider DRAM power. You shouldn't ignore DRAM power either. It's also quite important. If we break this down in a different way in terms of the types of data, we can see that weight stationary, as expected, has the lowest amount of energy per weights. Output stationary has very low partial sum weights, but it comes at a cost of increase in the other dimensions. And then row stationary is the only one that kind of optimizes across the total sum of partial sum weights and pixel energy. Right? So you again want to consider all forms of data when you're doing this optimization. One question we often get is, what about fully connected layers? We can show that you lose convolutional reuse for fully connected layers, but you still get at least 1.3x lower energy because you're exploiting those other forms of reuse with the row stationary approach. So very briefly, if you look at the overall picture, we can see that for convolutional layers, the RF, local storage, dominates. And then for fully connected layers, DRAM dominates because there's less reuse opportunities. But overall, in terms of energy, convolutional layers definitely consume more energy than fully connected. And you can imagine, this is for AlexNet with 5 layers. You can imagine as you go to deeper and deeper layers that convolutional layers become more and more important in terms of dominating overall energy consumption. Okay? So finally, we also built a chip. This is the work that was presented at ISSCC this year. This is the overall Iris chip. It has 168 PE, so 12 by 14 processing elements. It has a global buffer of 100K bytes, and then we do some kind of compression before we talk to the DRAM. We want to exploit data statistics in this work, so we know that there's this nonlinearity that basically sets negative values to 0. So we basically apply compression to this, and this reduces data movement from off-chip. So we get up to almost 2x reduction in data transactions from the DRAM itself. We also want to make the processing elements adaptive. So again, if there's a 0, we skip the memory access as well as the multiply and accumulate computation. And this gives us a 45% reduction in overall power consumption. So again, here's a die photo of the measured chip. It's in 65 nanometer process. It has 168 PEs and only 100 K bytes of on-chip buffer memory. Each PE has 0.5 K bytes of memory. It's 16-bit fixed point. And what I want to emphasize again is that it's highly flexible, right? So you can do many different types of widths, heights, filter shapes, number of channels, different strides, and so on. You need to have that flexibility to support these state-of-the-art neural networks, right? And so just to show in terms of benchmarking the overall performance itself, we can see that per different layers, the power consumption per layer will change, and that's because the shape will change. And also the number of processing elements that are activated per layer will also change, because you're trying to maximize this to make this as close as possible to 100%, but realistically, that's typically not feasible. The thing I really want to highlight here, since we're focusing on memory access, is that to achieve 2.6 gigamax of operations, typically for 16-bit inputs, you would need 16 gigabytes of data, input data, and you would generate 5.4 gigabytes of output data. But because we're really exploiting local reuse within the processing elements and then sharing data amongst the processing elements, we only read about 800 megabytes from the buffer. This is read and write, sorry, so number of accesses. And then we only read and write about 15 megabytes from the DRAM. So when we just quickly compare it to a GPU, for example, the TK1, I'll be very brief about this. We're an older process technology. We have fewer multiplies. We have about the same memory, have a little bit less. We're in 16-bit fixed, they're in 32-bit float. So overall throughput, we're about half of the throughput. The measured power, we're about 20x lower power. So if you say half the throughput, approximately 20x lower power, that's 10x improvement in energy efficiency. And also the DRAM bandwidth is lower because of the reuse. So now I'm going to show just a quick demo. So we wanted to integrate this into an actual real-time system to show that it can actually support. Okay, so this is the demo. It's integrated into the Deep Learning Cafe framework from Berkeley. It's doing 1,000 class image classification running AlexNet. So you can, grab an image of a dog. You can send it through this interface, again, through to our chip, which is shown running here. This is basically the PCIe Express that's connecting to the actual computer itself. Oh, that was pretty fast, but there was basically a third of a watt there. This video is available online, so you can slow it down and look at the power itself. But it properly, classifies the dog and the type of dog as well. The purpose of this demo is to show, again, that it can actually support these real-time networks. It can actually do all the configurations for all the layers in AlexNet. We've also measured it for VGG as well. Okay. So to summarize for this Iris work, Iris is a reconfigurable accelerator that supports state-of-the-art CNNs at below 300 milliwatts. It has an energy-efficient data flow to reduce data movement. It exploits data statistics for higher energy efficiency, and then we've integrated into the Caffe deep learning framework. If you want more information, including copies of the slides, you can go to my website or also the IRIS website. We have all the slides and the videos posted there. To tie everything together, because we talked about many forms of computer vision here, I just want to give the overall energy versus accuracy trade-off of all these different approaches. So this is in the same process technology, 65 nanometer. These are all measured results. This is looking primarily at the features, not the classification part, just for apples and apples kind of thing. So if we look at HOG, which we talked about, we're well below a nanojoule per pixel. But if we look at AlexNet and VGG, we can see that we're orders of magnitude higher. So even with all these optimizations for energy efficiency, as you linearly increase the accuracy requirements and introduce things like convolutional neural nets, you're exponentially increasing the energy requirements, right? So linear increase in accuracy maps, even for dedicated hardware that has already a lot of energy efficient optimizations, it's a exponential increase in energy. So this is something that we should improve on. And then just to summarize, so in today's talk we talked about energy efficient approaches, including things like exploiting sparsity through joint algorithm hardware design, minimizing data movement, balancing flexibility and energy efficiency. One of the key takeaways that I want you guys to think of is the fact that if you use handcrafted features, you can already design hardware and systems that consume the same amount of energy as video compression. So just think about what you can do with that. Basically, energy in that sense is not a limitation in terms of widely deploying this technology. And of course, as you move to higher accuracy, there's going to be an exponential increase in energy costs.